Okay, so we're going to learn how to solve logarithmic and exponential equations. Today we're going to start with a couple of logarithmic properties and rules, and then we're going to, I think the easiest thing to do first is actually solve exponential equations. So we'll do that first, and then tomorrow solve logarithmic equations. So a couple things though before we get there, some terminology, notation stuff. When working with logarithms, the most useful bases are base 10 and base e, okay? And because they are so prevalent and so useful, they actually garner unique names, okay? So when we have, and unique notation. So when we have a base of 10, we call that the common logarithm or the common log, okay? And usually, we do not write the base. You can kind of see it written right here. If it's just log of x, written that way, then it's an understood log base 10 of x. Okay? Kind of made the analogy last class that if I say my variable is y, we write it that way. And there's a lot of understood information. There's a coefficient of 1, and there's an exponent of 1, right? But we very rarely, if ever, write both those things together or either of those things, right? We usually just write y. Same idea here. There's understood information here when I write log of x. And that understood information or the agreement that we have is that that base is 10. Okay? Is that all right, everybody? Your buttons on your calculator are programmed with the common log. Okay? Just because of how frequently we use it. If we want to change the base, some of your calculators have the ability to go in and change that base. Others, we have to use what we call a change of base formula, which I'm not going to get into right now. Okay. The other base that is common, maybe that's a bad word to use. The other base that is used most frequently is a base of e. Okay, that 2.719 number. Okay. When we use the base e, okay, we call this the natural logarithm, okay? But the notation that we use is ln, and that is because of how we say natural logarithm in Latin is logarithmus naturalis, okay? So there's ln for you right there. Does that make sense? Okay, the notation, I think obviously it's easier to write. ln is easier to write than log, one less letter, right? But when we, in mathematics, create simplicity with our notation, I think we lose information, okay? So I've been doing this since I was your age, and I still do this practice to this day. You're going to see me in all the examples that we do. When ln shows up, I erase or delete the ln and I replace it with log base e. Because then I don't have to treat it as it's something different. I treat it just like all my other logarithms. Does that make sense? Okay. And I think it's useful or important to do that early on until you get the hang of what ln really means. Because throughout my teaching with students over 13 years, people think they're two different things, okay? They want to approach them and treat them differently. They're not. They're the same thing, okay? It would be nice if we never even had that notation, okay? And everybody just left it as log base e of x, and we moved on that way, okay? Going to show you some examples of this, like what we like to do with like things like ln of e or ln of e to the eighth. If I want to simplify that or evaluate that, basically what I'm going to do, and to prove to you that this is as easy as the other logarithms we've worked with, is when I see ln, I'm going to rewrite it as log base e. And then I have my argument of e to the eighth. So if I'm being asked to evaluate that, ultimately that means what is the exponent that I can take my base of e and raise it to? So what is this value that goes over here that will come back and give me e to the eighth? So what do I take e and raise it to so I can get e to the eighth? 8. And that's the reason that I change everything when I see ln to log base e, because I can't really ask that question or visually draw this picture if I just leave it as ln. Does it kind of make sense? Same thing on the next one. I see ln, not going to write it that way. I'm going to write it log base e. And then I've got 1 over e squared. And that 1 over e squared, I'm not even going to write that way. Because it might be hard to think about, what do I take e and raise it to so I get 1 over e squared? Can I rewrite 1 over e squared a different way? E to the negative 2, good. So now this problem looks a lot like the first one, right? So what do I take e and raise it to so it comes back and gives me e to the negative 2? Negative 2. And the last one, ln of 5. Okay, so ln of 5 is L or log base e. That's what ln changes to. And then I got 5. And you're going to come across these every once in a while. I'm going to ask you a question. If I take e and raise it to what number can I come back and get 5? So I take 2.7198. It goes on forever, never ends. What should I raise that number to so I get 5? Does anybody think in regards to irrational numbers and in regards to like multiplying and powers and exponents, that kind of stuff? It's kind of a hard question, right? Okay. So in this situation, you actually have to use your calculator. Okay, so ln of 5, that is going to evaluate to that number right there. So that is what I could take e and raise to the 1.60943791243. If I had more of it, you would get this thing closer and closer to 5. Does that make sense? But what if anybody at like the onset would have thought, yeah, 1.60943791243. I knew that's like the back of my hand. I knew that I raised e to that to get 5. Anybody know that?
Twice.
You knew that? Okay. So there you have to use your calculator. Okay. Questions on that? And I think that's just demonstrating the necessity or the logic of why I take ln and rewrite it as log base e. It makes things so much easier for me to make arguments and decisions and that kind of thing. Okay. The next thing I want to talk about are some properties of logarithms. Some properties of logarithms. And you've seen some of these in the past. If I take log, I'm just going to say base b of a times capital B. Do you guys remember seeing that that is the same thing as log base b of a plus log base b of capital B? You guys remember splitting those last year? Okay. Multiplication turns into addition in regards to the argument of a logarithm. Okay. So an example of that would be maybe, and let's just use the common log. We'll say log of like 2 times 3. If I wanted to evaluate that, that's the same thing as common log of 2 plus the common log of 3. And we can use any one of our calculators to confirm that. If we take log of 2 times 3, I get 0.778, right? Is that the same thing as log of 2 plus log of 3? Okay. Now, I want to show you the reason for that. Okay. So what we're going to do, I'm going to start with log base b of a b is equal to log base b of capital A plus log base b of capital B. And the first thing I'm going to do, I'm going to let this thing here, so here's the proof of this. We let x equal this logarithm right there. Log base b of A. And we're going to let y equal that one. Log base b of B. Is that okay with everybody? We know that to be true. I just identify or define those variables. Now what I want to do is I'm going to take this one here and we'll change it to an exponential. Would you guys agree that b raised to the x will come back and give me a? Take b raised to the x should come back and give me a, right? That's the exponential version of that logarithm. Can I take this one here and say b raised to the y is equal to b? That makes sense? It's just applying the definitional logarithm there. If I do a times, so now that I've got these, I've got a and b written in terms now of bx and y. If I take a times b, would you guys agree take that times that is the same thing as taking bx times by? Does that make sense? Okay. Would you guys agree that I'm multiplying like bases here? So AB could be rewritten this way. If I have like bases, what do I do with exponents? Add them. Okay. Now, what I'm going to do from there is apply the definition of the logarithm again. I'm going to say, okay, it's taking, our definition says log base A of x equals y if and only if a to the y equals x, right? So right now, this thing here is this version. It's the exponential version. Let's transform it back to a logarithm. So the base is b. That's that base right there. So this a is that right there. Does that make sense? So in a logarithm, it goes right there. Okay? That right there is the x plus y, and when I change it to the logarithm, it's the isolated variable on the right-hand side. So x plus y. And then the x, which is in our case the AB, becomes that right there in the logarithm. So I put AB there. Does that make sense, everybody? Okay. So now all I have to do is back substitute. What did we say x was at the beginning? It's log base b of a, right? So I'm going to replace that with log base b of a. We said y was log base b of b. And the left-hand side we see is log base b of ab. So you see that starts us with a product of an argument, ab, and it changes it to the sum of the two logarithms. Does that make sense? So that's the proof of that property. And all the other properties I talked about they have a similar proof, a similar procedure that goes along with it. But I know last year you saw these and you were probably told, just take my word for it. It's true, okay? But that's the logic behind why it's true, just the navigating through our laws of exponents and definition of a logarithm, okay? The other one is log base b of a divided by b. You guys remember what that turns into? A minus b, like that. So then, an example of that would be, log of 2/3 is equal to log of 2 minus log of 3. If you want to evaluate that on your calculator, you can see if that is true. In that top one, multiplication and addition go together, right? The bottom one, subtraction and division go together. And the final one is that the log base b of a raised to the c power. You can take that c out front and rewrite it that way. It allows you to get rid of the exponent there in the argument. So the idea there is if I have log of like 3 to the 5th, that's the same thing as 5 log 3. So just demonstrating some of these real quick. If I have log of 2/3, is that the same thing as log of 2 minus log of 3? See there, let's get this thing, there you go. So log of 2/3, because of the division, we can change that to subtraction. And then maybe a purpose of that is we don't like dealing with fractions so much. You know, we could change things into working with integers now. Okay. If we did, you know, the one that was like 3 to the 5th. Okay, so log of 3 to the 5th, that's the same thing as 5 log 3. You can see that those properties hold true with those values. You guys remember seeing those last year? Okay. I'm not going to get too much further with that right now. Tomorrow, those are going to play a pivotal role in how we solve logarithmic equations. We're going to have to address those first a lot of times before we can really get into the practice of solving a logarithm. What I'd like to do right now is actually get into solving some exponential equations. Okay. Solving exponential equations, I think it's enjoyable. Okay. Once you're able to solve one, you can basically solve all of them. They all work the same way, and it's just like solving any other equation. You're going to first isolate the variable term. Okay, so a lot of times, especially in the easy situations, that's already done for us. Then you are going to use the inverse operation of the exponential, which is our logarithm, to basically get our variable out of the exponent. Okay? And then once you do that, then you develop essentially what will be like a 1-step, 2-step, 3-step equation, something like a multi-step equation, and you'll just solve for the variable there. Okay? However, there are some questions that you can circumvent that procedure. Okay? Much like if I gave you, let's say 2/7 is equal to x over 7. Okay? You guys know that that's a proportion and you can cross multiply to solve proportions, right? But is there an easier way to find what x has got to be here? 2. X has got to be 2. That's called a 1-to-1 correspondence. To make the left-hand side equivalent to the right-hand side, the only thing that needs to change is the x needs to go to a 2. Okay? So that's a 1-to-1 correspondence. I would not want to waste my time saying 2 times 7 is 14. 14 equals 7x. Divide both sides by 7. X is 2. There's so much quicker way of doing it, right? So in examples like this, and we'll do it both ways, but examples like this, you're going to find out that the procedure I just kind of laid out for you isn't really always the best. And it's because in this situation, we have a base of 5 over here, right? Right now, this is a base of 625. 625 to the first power. But we should be able to take 625 and rewrite it so that it has a base of 5. Does anybody know what I need to take 5 and raise it to so that it becomes 625? To the 4th. Okay? And now 5 to 3x minus 2 is that side, right? Now to make these things equal, to make the left-hand side the same as the right-hand side, because the bases are already the same, don't I just need to do something with those, make those the same? So it's like that proportion I set up. All I've got to do here is say that 3x minus 2 needs to equal 4. X ends up being 2 in that situation. Does that kind of make sense? So if you're able to find and make the bases the same, do that, and then you can set your exponents to equal each other. Okay? You can do the same thing in this one over here, but is there a way to make, you gotta be thoughtful in some of these, is there a way to take 32 and rewrite it so it has a base of 8? No, because 8 to the first is 8, and 8 to the second is 64, right? We skipped over 32. So if you can't just augment one side, you got to think, can I do both sides? Can I get them both down to a common base? So I can get this down to 2 cubed would be 8, right? Now it's still raised to 2x. And then 32 is 2 to the 5th. Okay? Now in this situation, I think I would go one step further. I've got a power to a power there, right? You multiply. So you get 2 to the 6x equals 2 to the 5th, right? So now do we have like bases? So then if I set the exponents equal each other, I should be able to get x to be 5/6. So if you put 5/6 in right there, you'll get the exponent, which you raise 8 so that it turns into 32. That make sense? So the next one is just demonstrating that the exponents don't need to be linear. Like I said, x squared equals 16. So x could be plus or minus 4, right? Does that make sense, everyone?
Yeah.
That works. That's fine and dandy if you can recognize that you can make these bases into common bases. But sometimes you can't recognize that. Sometimes that's hard for people. Okay? So I'll give you an alternative technique. Now this alternative technique is going to give you a result that looks absolutely nothing like 2. But it will be exactly the same thing as 2. And we'll see that here in a little bit. So this example here. There is absolutely no way that I can rewrite 15 so it has a base of 2 using integers, right? Okay, going back to that question I asked at the beginning of class, does anybody know what I raise e to so that I get 5? Nobody knows that because that's thinking in irrational numbers. So this would be the question, what do I raise 2 to get 15? Nobody really knows that off the top of their head, right? Okay, so what we do here is first we isolate the variable term. Okay, so that's already been done for us, right? So if there was like a plus 3 here, or maybe a 3 times this, we would try to get rid of that 3. So we can isolate the base and the exponent that the variable shows up in. That make sense? It's already done here. Next thing we're going to do is, once we have it isolated, it's much like if I had like x squared plus 5 equals 10. You would isolate x squared, right? And then what would you do next? You would square root, because that is the what. Square root is the what of x squared? It's the inverse. So here, once I isolate the variable term, I'm going to use the inverse of the exponential. What is the inverse of the exponential? Logarithm. So we're going to use the logarithm here. And the way we do this is we say a to the y equals x, if and only if log of a, or log base a of x equals y. That's the definition of a logarithm, right? You apply that to this problem. So my base is 2. So a is 2. So when I transfer into a logarithm, that becomes the base over here. So I'm going to rewrite log 2 over base 2. Okay? This y is that right there, correct? And that, when I write it as a logarithm, becomes the right-hand side. So 5 minus 7x. And it says equals x. So x then, for our particular problem, is this 15. Which over here, when it becomes a logarithm, is the argument. Okay, so a moment ago, I was asking him, you know, the number that we take 2 and raise it to so we get 15. Does that right there, we're going to change it to a logarithmic notation, does that show up? Is that number log base 2 of 15? Is that representative of the number I take 2 and raise it 2 to get 15, right? So what I want you to understand, even though it's got a word in it, this is simply a number. It's a real number, okay? I think it's like 3.09 or something like that. Let's see. If I go log base 2 of 15, 3.906. That's the number that is right there, correct? Now, I'm not going to put 3.906 because then I change that number through my rounding, right? So we leave it as that. We leave it as the alternative symbol for that irrational number, okay? So if that's just a number, 5 is just a number, 7's a coefficient, right? Let's now take this thing and solve for x. So what would you do first over here to solve for x? Subtract 5, right? So we got log base 2 of 15 minus 5 equals negative 7x, okay? A lot of times, if you're a person that struggles with the word logarithm being over here, okay, maybe you go to the side and say, okay, I'm going to take log base 2 of 15. I'm going to change it to maybe round it to the thousandths place. And if I was going to solve that equation there in black, 3.906 equals 5 minus 7x, first thing you do is subtract 5, right? And you're going to get negative. If I subtract 5 from that, I'm going to get negative 1.093. Is equal to negative 7x, right? Okay. But you could also, maybe I didn't want to do that subtraction. Could I just written as 3.906 minus 5 equals negative 7x? Does that make sense, everybody? And that there is exactly what we have here. This is just log base 2 of 15. It's just a better way of writing 3.906. What would you do now to solve for x? Divide by negative 7. So we end up with x equaling log base 2 of 15 minus 5 all over negative 7. Not a real nice, concise format, but it is the best answer. Does that make sense? Okay. It's an exact answer. So now, just double checking this thing. So log base 2 of 15 minus 5 divided by then negative 7 gives me that number right there. Okay. Log base 2, 15 minus 5 divided by negative 7. Okay. I'm going to call that number A real quick. If I take 2 raised to the 5 minus 7a, oh, I don't know why I got a negative there. Sorry. So it's 0.5, positive. So now if I raise 2 to the 5 minus 7 times that number right there, does it give me 15? Okay. Does that kind of make sense on how to do that type of problem?
Is there a way to change the base like on a graphing calculator?
If you go to, so the answer to that is sometimes. Depends on what calculator you have. If you go to math, and if you're able to scroll down far enough where it says log base, then that'll let you do it.
Okay.
If not, there's what we call a change of base formula, which if we had time a little bit, maybe at the beginning of class tomorrow, I'll explain what that is. So let's come back up here real quick and do one of these problems. So let's say, we already know that this first one, 5 to the 3x minus 2 equals 6.5. We already know the answer to that is 2, right? Let's see if we can do the same process and get the same 2 by not changing the bases here, but by using that technique we just talked about. Because that technique we just talked about is how you solve all exponential equations. Okay? This technique I introduced at the beginning was a kind of special case scenario if you're able to recognize the bases can be converted. So I'm going to start with 5 to 3x minus 2 is equal to 625. And and you might find this being useful. Instead of writing the definition of logarithm over here on the side, I'm going to actually write it underneath. Remember we said a to the y equals x. If and only if log base a of x equals y. And I like doing that because I think now you can see the correspondence. You can see that a is 5, right? So when I come over here and write it as a logarithm, I better put 5 down there as the base. Okay. You can see that this y right there and this 3x minus 2, they match up. So over here in the logarithm, they are on the right-hand side. There. And then the 625 and the x, they match up. And over here in the logarithm, x is right there. That kind of makes sense on how to do that? Okay. So now how do you solve for x over here once you have this logarithm right now? Add 2. So log base 5 is 625 plus 2 equals 3x. And then what are you going to do to solve for x? Divide by 3. So right now, I've got x. Okay. Would anybody think off the top of their head that that is 2? Because that's what we said it was right here, right? But if I type that in, if I go log base 5 of 625, add 2, need parentheses here, and then divide that by 3. Does it give us 2? That kind of makes sense? My hope is that, like on a test or a quiz, it will say simplify as far as you can, evaluate as far as you can, right answer to the nearest tenths place, hundredths place, thousandths place, that kind of thing. So if you were to do this on your test and you wrote this, okay, my hope is that you would have taken your calculator prior to turning in your test aid and changed that value to 2. Okay? But nonetheless, we still get the same answer by going that approach. We okay with everybody? Let's see here real quick. We got it here, 52, right? 51. All right, let's look at, let's see here real quick. So I'm going to let you guys use Desmos. But let's say that you have a So you don't necessarily need to be able to do this on a test or quiz. But let's say that you had a calculator that does not support the ability to change the base. We have what we call the change of base formula, okay? Which basically says log base b of x is the same thing as log base a of x divided by log base a of b. Okay? Well, that's the change of base formula, which allows you to do exactly that, change the base. Okay? So, and usually what we like to do if we're coming across this and we have technology that isn't working for us, that doesn't allow us to change the base, our technology is programmed with the common log. It's programmed with a base of 10. So what we would want to do is we would basically say, okay, they're going to give me like log, I think the question we did was log base 2 of 15, right? Okay. And we would want to change that so that we can maybe use our calculator. What we would do is we would say log base 10, so the 15 is that top number. And then log base 10 of 2 would go there. And that would be the same thing as log base 2 of 15. Does that make sense? So if you're working on your TI 83, 84, and you can't change the base, and we wanted to work on this here, so maybe I'm struggling with this, maybe I'm just using the log that the calculator provides. So that's log base 10. So if I divide that then by log of 2 like that, does that still give me the same 0.156 number? Does that make sense to everybody? Okay. So the change of base formula might be a benefit in that situation if you don't want to either navigate to the function that allows you to change the base, or you have a calculator that does not exist. Okay. Tomorrow we'll spend time. We'll maybe introduce class tomorrow with another exponential equation question, and then we'll move into logarithmic equations. Okay.